instead of just calling
All right.
the program.
So I'm gonna show you my little shader. Okay.
But I wanted to avoid any loading. Like I wanted to make it so that there is no loading whatsoever. If the shaders become very heavy, they can take time to load.
Pipeline caches, they're fine. So do you have that link?
The iPad.
Okay. I can also give you like a stream link, I guess, because I just started streaming just for the sake. I'll send it to you on Discord. Discord. Right. Okay. Here it will be. Right, here you go. So I'll give you a rundown of how we designed our system, just to be fun. Okay. All right. So you see that there's a vertex shader and a fragment shader, and they seem to be quite long. But basically what you're looking at is a default vertex shader and a default fragment shader for an OBJ MTL loader, and that's actually trying to respect all of the different shading materials as best as it can that OBJ wants to implement. So, for example, if you want to override the inputs, like for example the locations, the attribute locations and so on, then you basically what you do is you make your own definition and then just define that up front and stick it to the front of the shader, and that would actually make this part go away. Same for the outputs. We have some includes, and here's a default descriptor set with our default parameters that are supposed to be provided by the engine. If you want to override like what that UBO has, or maybe where your model view projection matrix comes from, you can just define that and substitute your own declaration. And obviously if you want to like change the entry point of the shader completely, that's fine as well. And the more important thing comes in the fragment shader, where we actually do a bunch of things through functions. So here you can see the block which guards and protects the material definition. Actually, this is the BSDF, this part, and the BSDF is basically your shading model. This is the thing that I've been talking about, like your whether it's your your Lambert, your specular, or your hair, or your snow, like the different stuff that needs different BRDFs. Obviously you can see that we implement diffuse, we also implement specular, we try to properly weigh it and so on. Like you can see how we weigh it here. It's the same thing as the thing that I basically told you to use. And this thing that you see here is a correction factor, because the correction factor is actually different for every single value of refractive index, because the correction factor of 5%, the one that I told you to use, only applies if you are using a glass index of refraction, which is what you have hard-coded into your engine with that base reflectivity parameter. And obviously if you want to have your own BSDF cosine evaluation, then you basically you basically have to use two lines. You have to paste this and a forward declaration like this in front of the shader, and then paste this again like at the very end of the shader, and that will basically override the behavior. And we have our own compute lighting function. So if you want to add more lights or get lights that are different, then you can override that yourself. But the material stays the same, which is nice. So lighting separate from shading model, and also the main. So this is a forward renderer, but it'd be really easy to change it to a deferred renderer because all I need to do is just change this.
So if I do compile shaders at runtime, if I do compile it SPV at runtime, it means I will, the moment that we load any module, I'll need to recompile the entire thing.
Yeah, but that's the most efficient way to do it. Like, basically, it will keep your game running smooth. It's not gonna turn into like a slow, creeping death as you add more and more plugins because you end up having to do more and more image passes.
Yeah.
But remember, you don't have to.
Different shaders, but it's not like not every module will have that. But it's just in case that one module or two has it, we recompile the entire thing.
Well, only the shader that it wants to add to.
So only if there's a shader who wants to do it, we recompile it.
Yeah, pretty much. And the other thing is, like, listen, you don't need to throw the old shader away until you're ready. So you can recompile in the background. Like, first get all of the resources ready, including the new shaders, and then actually switch all of the stuff on.
Yeah, like I switch, I only keep it in the memory, write it in the file, keep it in the... I can compile it and keep the result in the memory and use that instead of writing the file.
Yeah, it's not like your game has to lag when like a model, loads or something.
If I load a module and it adds a shader, because I want to load and unload modules easily and like update modules without even restarting the game.
Yeah, it's not a problem. I mean, listen, swapping out shaders is just as complex as swapping out models.
Yeah.
Like, it's simple. I mean, don't delete while it's still in use, and don't wait to have it ready to show it.
But I make it so that reloading the entire renderer is instant, and I want to try to keep it that way. Like I press R to reload the renderer, and I don't even see a flicker. Like it takes less than a frame.
Well, but you're gonna be using shader pipeline caches anyway. So, I mean, the next time you reload the same thing, it's not gonna be a problem.
Sometimes I see a quick flicker, but not always. But yeah, the renderer, the entire renderer, like the device gets destroyed, everything. It reloads everything, keeps some stuff in memory, but nothing related to Vulkan. So it reloads the entire thing.
Yeah, so it's not a problem.
It will reload the shaders. Like when I do that, it will reread the shaders from file, bring them, but it doesn't compile them.
Compiling is actually not that bad. It's not that slow. Especially with pipeline caches. Like, pipeline cache can detect that the shader hasn't changed and just grab an old copy.
No, I'm talking about SpearV.
Yeah.
Sometimes it takes time.
To compile GLSL to SpearV.
Yeah, sometimes I compile multiple. It's long, but like if the shaders get complex.
Well, cache it. I mean, there's nothing stopping you from calculating a hash of GLSL source, and if the hash matches a SPIRV and a map, then use that.
I was trying to avoid having to link to GLS9 or to compile it to have it static in the engine.
It's not something that you want to avoid, because a lot of the time you want to use if-def and else to enable specific paths in a shader when specific extensions are available. And this is what you used to be able to do in OpenGL. Like, you do if def gl arb, I don't know, subgroup operations or something like that, you'd have a separate path. And in Vulkan, because you don't have the if defs, which can do like features at runtime, because the whole thing has to compile, so you cannot have a preprocessor that's dependent on driver features. What that means that you have to compile every single possible combination of extensions or like special hot paths, so you get combinatorial explosion. Like for example, we did this thing which does a really fast blur and sort and parallel prefix sum when you're trying to like count the number of elements preceding like a different element. Well, we've got like a histogram. And there's different extensions for NVIDIA, there's different extensions for Vulkan, there's different extensions for OpenGL, and there's different extensions for AMD. So it actually ended up being a shader which has 8 separate special cases for if def there is an extension. And if I wanted to compile a shader for every single one of the possible 8 on-off configurations, I'd have to compile 256 SPIR-V files.
So I almost have to like compile my shaders at runtime when I load the game, and if I load any module that wants to plug itself into a specific shader, I also have to recompile that shader as well.
Yeah, it's not as bad as it sounds. Like, especially if you are able to compute the hash of the GLSL source. So you basically don't invoke the SPIR-V compiler and you get an old cached version of the SPIR-V that was compiled.
Because I've had a hard time when I tried to link with the GLS9 library. I've had a hard time, so instead now I just call GLS9 validator to compile my shaders.
Do you use CMake?
Yes, I use CMake.
Okay, we've got it linked into our engine. I can link you the CMake that we used. But we actually use the whole SPIR-V cross. So that's a little bit overkill.
I only need GLSL. I don't want to go like I'm gonna give a standard to developers, and I don't. Anything else than Vulkan.
SPIR-V cross is pretty rad, even if you're only using even if you're only using Vulkan, because it enables you reflection on shaders. So you can query like, oh, what's in my uniform buffer? Oh, what's the name of this function? Oh, I'm using this struct. What are its members? It's pretty radical.
Okay, you got my attention.
That's okay. Actually
maybe that could be useful. Like if developers can write most of their logic and configuration in the shader itself, and then I can just read that instead of like.
We're conducting some research right now because we've got a really pesky AMD bug. It's where AMD does not honor the row major declaration on uniform buffers. It just basically, you write row major and AMD is like, fuck you. And this is a bug they've had in their drivers for 7 years. So AMD, fix your fucking drivers. And it basically comes down to this, that row major basically says that the memory is the other way around in the UBO or in the SSBO. And for a strange reason, AMD does not understand that, and it just loads the thing as column major all the fucking time. And we found a way to fix it. You know what the way to fix that is? And this only happens in OpenGL, by the way. I think. I don't know. I haven't tested Vulkan. The way to fix it is to make a dummy function, and before you read you basically make a dummy function which it returns the input argument. And if you take your SSBO or your UBO member variable and you just before you read it in the shader, you put that into the dummy function first. That magically fixes the AMD shader compiler that's in the driver.
Yeah, they only implemented the thing in some part of it, but not everywhere.
Yeah, like if you put it into a dummy function, then row major works. So we actually fixed it, and we provided an include file, and actually like the wrapper function to use every single time you read a matrix from a UBO or an SSBO, and that actually should have worked. I've tested it in RenderDoc, it works, but the problem is that we have an OpenGL engine like with a backend, but we accept SPIR-V only as input. So what happens is like whenever we have some GLSL that's in Vulkan dialect, we compile it to SPIR-V first, and then we down compile it to GLSL, and then that goes into the driver. So we noticed that the shader C compiler, which is GLSlang, is doing some optimizations or some mangling where when you're basically calling a function or something like that, it first saves the parameters as like dummy variables and then calls into the function. So we've got this problem is that it's intercepting our little wrapping function that makes sure that the row measure is loaded correctly. Yeah. So it first is reading the UBO or the SSBO into a temporary variable, and then putting that temporary variable into our little dummy function that fixes row major, and that breaks the fix. Because the very first touch of the variable which is declared as being in the buffer, that needs to go through the dummy function. So the thing that we're investigating right now is, because it's the fault of the SPIR-V that GLSlang generates. It's GLSlang that's actually generating all of this extra variables. So we're investigating how to make it and patch the SPIR-V with SPIR-V cross, with the information it gives us about the introspection into the shader, about the variable names and so on, all the reflection that SPIR-V cross gives us. We're trying to basically inject a function call into the SPIR-V, like intermediate representation. I won't really call it assembly, but yeah, we're basically trying to insert some opcodes so it does what we want first. But it gives really extensive information, like extremely extensive. It's so extensive that I can reorder my bindings in my descriptor sets. You can sparse.
I don't actually have to write the bindings. Like if I only I guess we could do the opposite with that. You could actually use what you wrote as descriptor sets and shoot it in your shader. You could do both ways, right?
Yeah. Like you can change the binding, the descriptor set, array counts, the functions that are being called. It's like it manipulates SPIR-V quite radically.
Okay. Well, that's interesting. So maybe I'll do that. So I'll erase the branch I made for that change there that wasn't working well, and I'll just wait till I do everything in the compute shader, and then for the post processing. Okay. I can do that.
Anything else I can help you with?
Yeah, HDR. Right now I'm using a very basic HDR thing. I want it to be like really very flexible and like with eye adaptation and all. And an eye adaptation that can be both automatic or manually adjustable.
Okay.
I already have Histogram, but it's basically a 1/16th resolution image that is already compiled. It's already being blitted down, and I can just use somewhere.
Mm-hmm. But so, this 1/16th resolution image, you still need to go through it and create like an actual histogram. So
So I guess we need a compute shader to do that anyways.
um, yeah, I have a compute shader that does that already. The way that I do
Oh,
it,
give it.
okay. Um, so the way that we do it is we actually optimize the fuck out of it because it's impossible to do it otherwise. I just need to switch to my old branch. Okay, where's auto exposure? That's the one.
Yeah, what I want.
So what we do is, well, first of all, yeah, okay. Okay, so we've got packed histogram, and we've got, okay. So, there's a whole bunch of stuff that's happening here that's going to be quite hard to explain. Um, but I guess we can try. Okay. So the very first thing is that I'm using a very large, very large block group, like the biggest I can make, maybe 32 by 32, because like the bigger I make it, the more efficient it's gonna be. So I'm processing 32 by 32 pixels at a time, and I've got my histogram, and my histogram is in shared memory. Because I don't want to be using like atomic counters or some other weird stuff like that to compute the counts of the pixels with that particular value. And the other thing that I do is I actually have this value called bin count, and it's not in here. But essentially what I do is, you know, like how there's, when you're using 16-bit floats for HDR, there could be like about 32,000 different values for, like 32,000 different values of brightness, right? Even more, but like let's focus on maybe only single channel right now. So it's a lot of values, and also that'd be a very big histogram. So actually what I do is I don't really care about like how much pixels there are at like a specific brightness, more about like a set of brightness ranges. So I use the fact that the IEE 754 standard is ordered so that if you cast the floats to integers, if you sort them, they will be going actually from smallest to largest. If you get what I mean. So basically, the high bits in the float pattern, they actually make the float bigger. So instead of looking at all 16 bits of a float for the histogram, I only take the very front bits. Really, I'm only looking at like exposure, like the exponent. I'm not.
The magnitude.
Yeah, I'm getting the magnitude. I'm not really looking at the mantissa, really.
Yeah.
I'm only looking at the exponent. So this variable that you're looking, this bin count is most probably like maybe close to 1,024. It's definitely not 64K, because again, I don't want to be using that much shared memory. You know, like there's only about 16K of shared memory to go around. You want to stay underneath that, and shared memory can only be units or floats. So, you know, no more than 8K bins, and you know, 2K and 4K works maybe better. So and also to ease the atomic counter, even though it's in shared memory, when atomics are incrementing the same variable, then we have a conflict, and you don't want that. So in order to ease the contention, I actually do a local replication here, and you can see that the local replication power is free. So it means that I replicate the counter 8 times, just to ease the atomic contention on the counter when I'm going through the stuff. And there's also like a little +1 here on the padded bin count. It's to do with this thing called there's a thing called bank conflict. So yeah, so basically I'll have to explain how compute shader works really to get to that. But it's nice to make sure that within a subgroup, which basically like within a multiple of 32 or 64, like if you were to partition your work group into such things, it would be nice to make sure that you're accessing different shared memory banks. So this +1 makes sure that, you know, like as you go through the replications, you basically shift off by 1, so you always misaligned, so you're never hitting the same thing, even if it's the same value. So the very first thing that we do when we enter into main, we load our color value from the texture. I have to compute the texture coordinate from integer coordinates of the compute invocation. It's not that hard. It's basically, you know, this is actually like a little input that I have, but I'm scaling a texture, but you can just disregard this part. I'm basically getting I'm basically getting the global integer ID, putting it into a float, and then dividing by the texture size. And then I'm clearing the histogram, because obviously shared memory starts off uninitialized, and you need to actually clear it to some value by yourself. So I'm obviously clearing it using all threads at once, because shared memory is shared. So I've got the count of how many threads I have, and I've got an unrolled loop here. So it's basically clearing out all of the memory as it needs. Obviously, there is a little bit left over at the end here, just to make sure that you know, I don't write outside of the bounds of the shared memory. And whenever you do this sort of cooperative group work, the groups can be the threads can be running out of sync. So whenever you want them to sync up, as in proceed to the same point and make sure that all of the threads are done, you use a barrier, and this is an execution barrier, and that makes sure that the execution has actually completed of all of the threads. But to make sure that the memory writes actually go through the caches and they will be visible on reads from different threads, you also need a memory barrier. And there are different memory barriers from different sorts of memory. You know, there's different barrier for images, different memory barrier for buffers, and obviously there's a different memory barrier for shared memory. So after we clear the histogram, we get our color value and we decide which bin to put it in. And you can see the put in bin little thing. So here, when you do this put in bin thing, I calculate the luminosity of it. I don't need to do red, green, blue histograms. I only need to do luminosity histograms. And you can see that I'm extracting the exponent here, because it's a shift by 23 bits, so it means that I'm clearing away the mantissa. I'm also dealing with the exponent bias, and I'm adding a little offset to it. I don't know why, but that's what I'm doing. And this value that I get from the exponent is between 0 and 31. And I'm shifting it 10 bits left, and I'm actually getting a little bit of the mantissa, just a little bit. Because remember, this luma value that I got was actually from a 16-bit float color value, not a full 32-bit float color value. So the exponent in a 16-bit float is actually much smaller. Yeah. Oh yeah, this is a conversion. This is this is all commented out. Sorry, my bad. Okay, so this is my luma bits. This is 32 bits. This is 32-bit float. And here, yeah, you can see me shifting by 13 bits down. So I'm throwing away 13 bits of the mantissa. And then I'm throwing away as many bits as I have the histogram power of 2 rows. So this is gonna be... This actually gets fed in by my little example.
But what kind of luminosity range are we talking about with
a full 16-bit. So anything from 1 over 64K up to 64K. Or 32K, actually. I don't remember.
32K.
Yeah, so it's pretty big. It's sufficient.
So
Even
it
if
will
you
be sufficient
yeah,
for, but I'm.
even if you're gonna be using 32-bit HDR, you can still do the histogram as if it's a 32-bit float. So as if it's a 16-bit float, because you're only looking at a little bit, mostly the exponent, and a little bit of mantissa, like a little bit.
Well, I use 16 bits anyway, so your thing is taking in a 16-bit image. It's taking the image, the scaled down image, or the original image?
A little bit scaled down, but you can also take the original image. Basically what you want to avoid, right? What you want to avoid is when you have an image which is like, think of a chain linked fence or like a checkerboard, and like let's say some really bright light is shining on the links in the fence, and behind that it's pitch black, like it's at night, or any sort of other like checkerboard pattern. What you don't want is you don't want to downscale the image so much that instead of getting the bright fence values and the dark background values, you get like this middle gray value, because then when you do automatic eye adaptation, you're not going to adapt neither to the black background nor the fence. You're not going to adapt so you can see the fence clearly, and you're not going to adapt so you see the background clearly. You're gonna like adapt to this middle gray, which is completely useless. So what you want to do is you want to build a histogram and then pick out the median value, not the mean. You want to pick out the median, the most common luminosity, and then adapt to that. And this is how we build a histogram on the GPU.
If I use that, I can just plug in there my full resolution image instead of having to build a smaller one.
Essentially, if you want this to be fast, then there's nothing wrong with scaling down the image maybe half in each dimension, or maybe 4 times in each dimension, because you're not really expecting to have like 1 pixel checkerboard.
Yeah. Okay, so 4 would be good then.
Yeah. I mean 4 in each dimension would be fine, and then that would make sure that the pixels still don't average out. And the other trick that you can do, instead of downscaling, or maybe downscale a little bit less, is to only care about like the center area in the image. Well, not the center spot, but I'm just saying like maybe like the inner 10% or the inner 25%.
Okay, so I could I could just blit the image, and in the blit I could just select the area, like maybe.
Yeah. Select the area and then downscale it as well.
I take half. I take half, and then I can even scale it down by 4 after that. So
exactly.
It would be scaled by 8.
Yeah. Exactly. That'd be nice.
Yeah. Okay. And it would be so I only take the half, like the center of the screen, what the user is looking at, and that's where I take. Yeah. Okay. Well, I can play around with the.
Yeah. So you basically take a little bit of the exponent, or most of the exponent. You take a little bit like the higher part of the mantissa, and you use those bits. You shift them down, obviously, and then you basically use that to index into the histogram. And you do an atomic add +1.
Yeah, and then the tone mapping itself, that will go with that. How will I do that?
Yeah. The important thing at the end, when you've done your replicated histogram, because you can see that I do this little thing where I make sure that different sim planes from different, like let's say this is your thread group. I'm using a thread group, like let's say for demonstration, like 8. I basically make sure that every other one gets its own buffer and its own address to do atomic add to. Basically, it prevents this scenario when I've got like an area in the screen of uniform color, and all threads are trying to add to the same shared memory address.
Because basically, what we need is average out that histogram and get what's the.
No, this isn't about averaging out. This is just about atomic counter contention. So if all 8 of them are gonna be trying to write to the same.
Oh wait, 8 what? I'm not sure.
Okay, threads that are running on the GPU simultaneously.
Oh, threads.
Yeah.
Okay.
So if all 8 of them are trying to write to the same atomic counter, they're gonna have to serialize and run serial instead of parallel. So what you want to make sure is that they write to different addresses, so then they can still run in parallel. And that's how I do it with this little replication thing. That's why I replicate the histogram.
Okay.
So every 8th invocation in the compute shader gets its own gets its own histogram, and then at the end I merge the histograms together.
Okay.
That's an optimization.
Okay.
Yeah, you can just use one histogram, but it's just gonna be slow. Yeah.
Okay.
So after the barrier, I merge the histograms together, and then I do like an atomic add from the. I do an atomic add from the computed value that I computed locally, because there's a local histogram, right? So there's a local histogram which is only like a histogram for the values within the block, within a 32 by 32 pixel area. And then I don't copy, but I add the whole histogram to like a global histogram. And that's how I get the global histogram for the whole image.
That global histogram basically is like one float, right? Or 3 floats?
No, the global histogram is a couple thousand floats.
How do you... Well, you need to process a final value or color or a scalar.
Well, the histogram, because the histogram is like, let's say... values between 2 to the power of minus 5 and 2 to the power of 4. 2 to the power of minus 4 and 2 to the power of minus 3. And I'm getting basically a count of all the pixels which have the value in that range. That's the histogram.
You get range, right?
For every single value range, right? Tiny little value ranges, I get the count of all the pixels that are in it. That's why I'm saying I've got a big histogram, and then once I've got that big, yeah.
But then, like, to apply the tone mapping, you need like one value to do the adjustment.
Oh yes, exactly. So, so what I do is I do a parallel prefix pass. So what I do is when I do the tone mapping, I do some redundant work because I don't want to do another compute dispatch. But what the block group does is it loads the global histogram into shared memory, and then it sorts it. It doesn't sort it, but it does a cumulative histogram. Like, you know what a cumulative histogram is?
Cumulative histogram, I guess it's the accumulation of all the values.
Yeah, like for every single value, you add all the values before it. It's like a cumulative distribution in maths. So it's a running total.
Yeah. Okay.
So you have this. So first we read the values from the global for the whole image from the previous, because this is the second. This is now the second compute shader. So we're reading all of that into our shared memory, and we are also zeroing out the global histogram for the next frame, because we don't want to have a separate clear shader for that. Because that global histogram needs to be cleared to 0 before we proceed. So now we've got our global histogram in shared memory. And basically what we're doing is we're adding the values together, across thread invocations, and then we're doing a parallel prefix pass, which isn't the fastest in the world, but the amount of work to be done here is actually so little that it wasn't worth optimizing. So what parallel prefix scan does is it will use parallelism to use all of the threads to actually compute this running total. It's quite it's an advanced algorithm. I think I can link you a paper, I guess.
Or you can send me that code.
Well, it's on GitHub here.
Yeah.
Yeah.
It's open source.
Yeah, all of it.
So that's from your engine.
Yeah.
Oh, can you send it through Discord?
Okay, no problem. Yeah. So afterwards we have this parallel prefix pass, and that actually gives us a running total of all of the pixels that have it changes the meaning of the histogram, because before the histogram, what is the count of all of the pixels with this particular brightness? Now it's giving us a count of all of the pixels with this particular brightness or less. So how many pixels there are with a brightness that's less than this. And what we do is I actually have a upper bound. It's a parallel upper bound. So I'm actually able to multi-thread your common operator from C++, which is called std lower bound. And I'm actually doing a lower bound with multiple threads. Yep.
I'm looking at your CPP. So you have basically a wrapper around the graphics API.
Yeah, pretty much. So yeah, you can.
It works with Vulkan and OpenGL.
Right now I only have OpenGL, but I want to move to Vulkan. Yeah. So here you can see that I'm doing a branchless binary search. This is how you do a binary search with no branches. And yeah, basically I'm using two threads. I'm using one thread to find me the upper bound and the lower bound. Sorry, the upper exposure value and the lower exposure value. So the way that I do it is I find the upper percentile and lower percentile. And then because
so you get two bounds.
Yeah, I get two values because I'm not getting the median. I'm getting like the 45th percentile and the 55th percentile, so a little bit on each side of the median, and then
because you want to expand your exposure to see more things.
No, it's to do with temporal instability, because when you're picking a median, the value can jump erratically.
Okay, but if you
Yeah, and now I'm picking like a little bit below the median and a little bit above the median, and then I'm doing the arithmetic average. So the arithmetic average is basically if you took two magnitudes of two numbers and then took an average of the magnitude. So if it's an average in log space.
Okay.
So I multiply them together and I find the square root. Basically, that's an arithmetic average, and that's actually that's the luma value that I choose to adjust to.
Okay, and then that code, that last shader.
Oh, the last shader. Okay, so
the one that does the tone mapping math that converts the vectory.
Okay, so it's a little bit split because I always like to optimize. So I use here like a modifying Reinhardt operation, or maybe like no, sorry, I use a yeah, maybe it's modifying. I basically I've implemented tone mapping with 3 different operators. One of them is the Reinhardt operator, which is fairly simple. One of them is Reinhardt with burnout. So when values are allowed to be mapped to values higher than 1, where you want to have like burnout in your images. And I've done ACES, which is the one that they use for filmmaking nowadays as a standard. And that's a standard for HDR video as well, for publishing. And I've also used like this exponential tone mapper, which isn't really like based or anything. And essentially what I do is I pre-compute some constants that I'm going to use later that are going to be the same for the Luma, and I store them in an SSBO. Like I actually call this output to UBO, but basically here the buffer is bound as an SSBO.
Put that in push constant.
What?
I'll put that in the push constant.
Well, I'm writing from a compute shader, so the only buffer that I can write to is an SSBO.
Oh, you write that from the compute.
Yeah, I write that from the compute into a buffer through the SSBO route, and then I use that SSBO as a UBO in the shader that does my tone mapping. So basically here I just pre-compute some constants that I later need for the equation. And when I do my tone mapping is just simple. It's beyond simple.
The way I would do it is get that value out of the UBO. I'm bringing it to the CPU side because I would do that algorithm. All these compute shaders, I'll run it in the slower compute thread. Like since my renderer is multi-thread, I have a slower thread running for operations that don't need like really real compute.
Yeah, but this value that value does not need to come off the GPU at all, like because that include that in like whenever you need to read something back from the GPU, that introduces like a sync point or some sort of latency, and like if it can.
I could just calculate it on the CPU side and then send it as a push constant to the shader that would actually.
No, that's gonna be much slower. Like you want to make sure that the data that like you don't even want to bother the PCI Express bus for transferring like 8 bytes across.
Yeah, well, how do I do it? Because I don't like. I'd rather do that than calculate the whole thing, like everything. These compute shaders and all. I don't want to calculate that every frame of the main rendering thread. I'm gonna render that in a separate thread.
Like I do this in OpenGL, and that takes like 50 nanoseconds. Oh, sorry, microseconds. I profiled it with a timestamp. It tone maps a 720p image in 50 microseconds.
So I could do it in like the same. Can I do all of that in one compute pass that does everything else as well?
You can merge the first shader into your shader that writes out the history buffer, maybe. Not really, because you want to downscale the image. But you could merge the first pass of that whole shader stack into the image that maybe blurs, does the Gaussian blur for your bloom.
I don't have the bloom yet, but okay. I will do it at some point.
All right. So you wanna you could merge it with something that already is using the downscaled image.
There's nothing that is using the downscaled image yet, except
then you can't merge, because like all of the blocks that calculate local histograms, they need to finish computing the local histogram, and they need to finish writing the atomic global histogram. They need to finish
Well,
increment.
I need to render it in a separate compute pass anyways.
Yeah, separate compute pass dispatch, and then a memory dependency, execution dependency, another dispatch to just one work group to calculate the exposure factors, and then the tone mapping.
So right now I'm using 3 render pass, and I will need to convert that into 3 compute pass anyways.
I wouldn't call them passes, just dispatches. I mean, a compute dispatch is as cheap as a draw command.
Yeah. Okay. Oh. Okay. So. Okay, so instead of recompiling the shader to add some stuff in the compute, I can just add more compute shaders. It'll be cheaper than adding more render shaders.
No. Because what you were asking me before had this whole chain of shader A writes output, shader B reads output of shader A, produces output, shader C.
No. Those are only three pass. The sub passes do that, but in between each sub pass, they can just.
I can say as long as compute shaders are touching completely different data and they're not introducing a redundancy to the reads and the writes.
Oh yeah, well that's the point. They need to add. I'm using blending in the first and third. Post processing pass, sub pass, the same render pass, 3 different sub pass. In the first and the third, they basically add blend. They add up with alpha blending to the final color, so they can in that sub pass, all the draw calls can just run on top of each other and blend together. It doesn't matter. It's so that was the point. If some developer want to add some specific post processing that blends something on top, they just add a shader.
I would keep the tone mapping like a separate thing, because tone mapping you don't really want to add to.
Yeah, well, I thought doing it in the second pass, the calculation of that tone mapping, but then I apply it in the third pass. Well, the histogram calculating it in the second pass or in another thread, but applying the tone mapping in the third pass as the first.
Yeah, but the thing is, you need your whole completed frame to compute the tone map for it. To compute the histogram.
I have yes. If the frame is complete, it has it's lit and all, and it has the first post processing, which the first post processing subpack will contain TXA8. No, not true. Not TXA. It will contain. The
okay. Listen. You need the frame after TXAA. After TXAA.
It is.
And then you need to. Yeah.
But I'm rendering my thumbnail that I call it. Okay. In the second subpass, I do TXAA, and then I write to my history, and then I wanted to take that history image and scale it down, blit it to 1/4, and then take that. That will already have the TXAA on it.
Yeah, and then that you can histogram.
Exactly. So that's how I structured it, and then after having done that, I do the HDR. I do the third post processing pass where
actually. Wait a second. You can merge, because eye adaptation you want to blend over time, so it's not a problem to use previous frames eye adaptation. So you can.
No. I'm doing the eye adaptation. I'm doing the histogram before applying any tone mapping whatsoever.
Yes, but I'm saying that you can. Okay, so bear with me 1 second. in your TXAA, after you write the history buffer and also write to the swap chain in the same shader, right? You can do the tone mapping when you're writing out to the swap chain. So your history buffer is HDR or whatever, and your swap chain is LDR, and you're tone mapping to that. So you're writing out your history buffer to, well, you're writing out your values to your swap chain, and while you're writing them out, you are tone mapping them, but the exposure values that you are using for tone mapping, they come from the previous calculation of histograms.
Yes. But I could do that in a separate thread. I was thinking of actually taking that, because I generate basically, like I have
That's
a
not going to
history.
improve anything.
Why?
It's too little work to send off to a different thread. Plus, it's much better to do like what I said, with the fact that because
otherwise it will wait for the other thread to finish.
you will be like, the queue management will be a bigger cost than the speed up from scheduling it possibly asynchronously. And the biggest thing is,
I don't know how heavy it is, so
it's like I just told you, it takes 50 microseconds.
Okay.
Unlike a laptop GPU. So
Okay. Then I guess I can do it in the second pass.
and
like,
this is the important thing that I just told you, is right now, look at the camera. I'm here. So right now what you have is you have TXA, well, not right now, but what we just talked about is TXAA, downscale, histogram, more histogram, the prefix, parallel prefix, tone mapping, output to swap chain. So you can see this is like a big dependency. And now what I'm saying is what you can actually do is you can do TXAA, inside the TXAA, do the tone mapping with the previous frame's histogram. So you do the tone mapping with the previous histogram, you output to swap chain here straight away, and then the image is already on screen, and now you actually do the histogram of this previous image that you're then going to use for exposing the next frame. So that cuts down the time it takes you to create an image and put it to the display.
Okay, but that would be in a compute shader, right?
Yeah.
Okay, so because I need to plan for SSAO and potentially like screen space reflection and all other kind of screen space post processing that developers can add to. Okay, so that path could be a normal render path, rasterization.
Yeah, that needs to go before TXAA, and it cannot be merged with TXAA because TXAA does this whole offset thing.
It goes before TXAA.
Yeah.
Yeah. That pass is completely before. It does everything before TXAA, and that I can leave it as is.
Mm-hmm.
Then the TXAA pass, I could do compute that does everything else as well.
Mm-hmm.
Is that right? But then that compute pass will need to, like, because I wanted to do TXAA, and then after TXAA, after having the TXAA, the image, I could do the tone mapping and then bloom and other lens effects.
No. Bloom and other lens effects, they go before tone mapping.
Okay, before tone mapping, but after TXAA.
Yeah, after TXAA.
So just before tone mapping. Okay. So tone mapping would be done then.
You could do tone mapping while you're doing the bloom. Do combined bloom and tone mapping, because tone mapping is incredibly simple. It's so simple I'm struggling to find the shader actually for it. Where's my shader for tone mapping?
Okay. So then after the tone mapping, that could still be in the compute shader.
Yeah, the bloom needs to be in a compute shader.
Needs to?
Well, I mean, all of this stuff that you can read online about,
I know.
Gaussian Gaussian blur, separable shader, and like, oh, I'm going to optimize my Gaussian blur by taking some samples and using a linear interpolation on a downscaled texture, and I'm gonna do what Godot does, and called generate mip maps, and then like stack 4 mip maps on top of each other to get like a large bloom radius. All of that is basically last generation bullshit. What you want is summed area tables and the central limit theorem. The central limit.
Can I just do that inside that second post-processing path, like that compute path that does the TXAA? Can I also compute at the same time as computing the histogram? I can also compute like a bloom filter with that.
Not at the same time you're doing the bloom, because the bloom needs.
Because it will take the same image, the same scaled down image.
Yeah, but it's different. It's different work groups arrangements, because when you're doing a bloom, you need your work groups to be to be like straight lines along X, one dimensional. And then when you're doing the blur, the other direction, you need like straight lines along the Y. And then when you're doing actually that's not a problem. Yeah, you could do the histogramming actually while you're doing the bloom.
Might as well
go
through pixel that scaled down image.
Yeah. That's not a problem. Yeah, but for the bloom you need at least two compute shader dispatches.
Well, yeah. The first one to generate the image to have for like the
blurry, okay, that's free now.
Huh?
No, that's at least two. At least two. You need one to downscale and blur along X, and then you need another one to blur along Y. You do it separable.
So that's a Gaussian blur.
Well, it's a separable blur. Doesn't matter if it's Gaussian blur or if it's box blur or if it's, I don't know, whatever symmetric kernel you have.
So it needs to blur one side first because it needs to have finished blurring it to actually do the other.
Yes, and you also want to use a shared memory in a different configuration. You want to use shared memory to store rows in the first blur, and then you want to use shared memory to store columns. We actually have a very fast example in our engine of how that works. It's called a constant time Gaussian blur. I can do a blur 512 by 512 in the same time it takes to do a blur of 2 by 2, and that also runs in like sub millisecond times.
Okay, that's not as important. The bloom is not as important. I was just a little curious because I'll need to be able to support these kind of things. But it's very low priority. I can still do that in 2 years. Right?
Mm-hmm.
But what's more important would be the HDR and like tone mapping, histogram, and that would be the most important next. But that's really my next step, and I need to make it work well with my PBR lighting. I need to make that work well and generate realistic light values, and then use the tone mapping to histogram and do the adaptation, the auto exposure thing, and I need an auto exposure that we can also happen to manually adjust.
The best way to adjust auto exposure is to be able to modify the value that was computed from the histogram, like multiply it up or multiply it down. It's not really that useful to substitute that value for your own.
Yeah.
That's I found my tone mapping shader actually. It's 34 lines. So all I do is just get my parameters from a UBO, and I just use that for my tone mapping function. Tone mapping function is very simple. You basically take a color, you calculate its luminosity, and then you apply a transform just to the luminosity. So you basically you subtract the luminosity for a new luminosity.
Okay, and then the like uniform, you have dynamic resolution scale and auto exposure inputs and auto exposure parameters. Wait, so you have two sets of vectors. I'm not sure.
Yeah, I'm only using the last one.
Oh, the first one is not used.
Yeah, it's because I'm using the same thing as a SSBO and a UBO. I need to like make sure that the packing is the same with the regards to the offsets. So I need to leave some space here for the compute shaders because they're all right into the same buffer. That's
Okay,
what.
so then your vector auto exposure parameters, that's what you use.
Yeah.
It contains term, divisor term, and average luma, and then you use these values for to calculate tone map, and I guess dynamic resolution scale text score. Okay, text 0 will be the input image, I guess.
Yeah, exactly.
And you just output tone map AXT with APR val, which is texture.
Yep. So for this part, you basically can get different functions. For this is a bad function.
Why do you use texture LOD and not just texture?
Because texture LOD makes sure that I always sample from mipmap 0, like when I do it like that. I basically try to be as explicit as I can and not give the not give the GPU a chance to fuck up.
Because the GPU could decide to take another mipmap.
Yeah, it could decide to take another mipmap, especially that I'm scaling the texture. There are no mipmaps there, but if they were, because I could be using a texture that has mipmaps as a storage thing, then I would just want to make sure that I get the base level.
But I'm not sure if there's no mipmap, will it actually fuck up, or it will know there's no mipmap?
I have seen things like AMD GPUs, and they're wonderful shader compilers. So, like, with regards to writing shaders, you need to treat the GPU as dumb, and the guys who wrote the driver compiler as even dumber. Don't count on the compiler to unroll loops, even if you can plainly see that it's going to do a constant number of iterations. Don't count on the compiler to, for example, if you're going to pass an array to a function, and then that function is only going to get one member of the array, and which member is going to get of the array is constant. Do not count on the whole thing to get optimized so that the whole array doesn't get copied through to the function, and so on and so on. The list is long.
Okay, I'll meet my girlfriends.
All right.
Okay.
So, I guess that's it.
Yeah. Okay.
All right. See ya.
Okay. See you. Thanks. Bye.